Do you hear me? If you can't hear me and the others can, let's check your speaker. All right. I copy here some information. I was asked, what about the test 2? On the lecture with somebody, I also talked about the number of exercise in the test 2. It will be one seesaw and one pure rolling like this. So from now, because your physics background can be different, we will practice on the seminar how to solve these examples. Are you okay with that? All right. So, what should we know about torque? Torque is a vector R cross F. How to calculate this vectorial sum? So this is R, this is F, like X, Y, and this vector will be the torque. So if the motion is in one plane, for example, the plane of your screen, it's a bit easier to calculate this vectorial multiplication, since if you put the origin in the axis of the rotation and the force acts here, the R, the position vector of the start point of the force, is the vector from the origin. You can't see my drawing. Oh, yes. This table is worse and worse. Let me check whether it's frozen. Oh, here. Yes, you're right. Just a minute. The Bluetooth communication stopped. Thanks. I connect again. New link is in Discord. Let me see. Tau equal R cross F. Well, still nothing. Yes, oh, yes. All right, so if we rotate something in the plane of the table, for example, this is the origin and this is the axis of the rotation. If I have a force here, wow, it's slower and slower. All right, so if the axis rotation is here, let's wait a bit. So we can forget this table if it's too late to show anything. And if you open this link, can you see my drawing? Because here I can't see, but on my phone I can see it. What can you see? Here I have a drawing. Do you see that? Ah, I supposed. Oops. Yes, it's reconnected. I see. Lost internet connection. Check the connection settings. The session will expire soon for all participants. One last chance. What about the YouTube? Do you see me? Do you see my cursor, for example? Can you hear me without any lagging and so on? Is it okay, the YouTube? All right. So final try. So 1, 2, 3. All right. Let's forget that. Oh no, the 1, 2, 3 is there. Clear it. 4, 5, 6. Oh, all right. So the torque is a vector. This vector we can use like F equal m times a. This is for translation in in rotation, we use the torque instead of F. Instead of mass, we use the moment of inertia, and alpha is the angular acceleration. So this is the dynamical equation for rotation. How can we use it? So, and by the way, if we have more forces on a body, like F1, F2, F3, we have to calculate the sum of the torques. And we can calculate the sum torque, and this sum will determine the angular acceleration via moments of inertia. The easiest example is the balanced seesaw. So, if this is a massless, and we put an M1 here and an M2 here, this is the origin of the coordinate system, this is the axis of the rotation, goes through this point. Here we have a weight, G1, and here we have G2. R1, R2. Since this is 90%, the tau 1, which is R1 cross G1, because of this 90 degree, sorry, not percent, 90 degree, and since they are in the same plane, that will be simple R1 G1, and the direction of the torque will point to you from the skin to your face. So let's say this direction. And you can use your right hand. So if this is R1 and this is the force, this is the position vector and this is the force, the direction of the torque will be like this. So if you come here with your fingers, R1 force, that will point to you. Alright, what about torque 2? This is R2 cross G2, R2 G2, and the direction will be point behind the screen, so from your face towards to the screen. What does it mean? Let's choose a positive direction. For example, positive direction points to you. In this case, the sum of the torque is a plus torque 1 minus torque 2, and if this is 0, this seesaw is balanced. Still some missing characters, so oh yes, it's there. All right, how can we use it? For example, let's put an M1, let's say 10 kilogram, on the radius 2 meter, and if this is 15 kilogram, the torque 1 is 100, so G will be 100 Newton, 100 Newton times 2 meter equal 150 Newton times R2. So R2 will be 200 over 150, that will be about 1.3 meter. This is a much more interesting ladder example. Please check it. It has some very practical advice how to solve this example. One other thing, so this is for rotation. What do you know about translation? Since you have a system here, which is the mass 1, mass 2, and the massless seesaw, and there are two forces, the two weights points downwards. So that was the rotation. From the dynamical equation of the rotation, we know what is the R2 we need to be balanced, but that's only for rotation. Let me show you what I'm talking about. Here we have the seesaw, mass 1, mass 2, G1, G2. This system, if you look at it like a system, its net force, the sum of the forces right now, is G1 plus G2 if this is the positive direction. This is non-zero. Why? So based on this equation, there should be some m1 plus m2 times a, should be some acceleration downwards. How can we guarantee that this seesaw does not accelerate it downwards? There is a so-called reaction force here. Let's write R, and this reaction force has to be equal to G1 and plus G2, and its direction is upwards, which is minus. That extra reaction force can guarantee that there is no angular acceleration, that there is no acceleration. So the previous torque example can guarantee that there is no angular acceleration, and this reaction force should guarantee there is no acceleration. So we will do that in the next example also. It's not enough only writing the equations for the rotation, because with this R we have to fix the translation. But what does it mean? Can this R rotate the system? You can answer in this code. Will it cause any rotation, this reaction force? If yes, why? If not, why? Will this R rotate this seesaw? The answer is no, because this force goes through the rotation axis, like putting this force here, and if this force goes through the axis of the rotation, that means the level arm is zero, since the level arm is the distance between the force vector, technically between the line of action, plus the origin. If this force goes through the origin, through the axis of the rotation, it can't do any torque, it can't rotate a system, because the D will be zero. So for any R can be anything. In this case, R is the nominal value G1 plus G2, which is 250 Newton. Even it's a 250 Newton, well, I have to write more clearly. G1 plus G2, which is 250 Newton. All right, that's the seesaw example. Right now, you can solve one other. Let's take a picture. Again, this example is exactly what you will find in the text too, or at the exam. Massless seesaw. I put an M1, which is 15 kilogram. R1 equal 2 meter, and I put another one, M2 equal 10 kilogram. What is the R2? Where should I place a 10 kilogram body? On the seesaw if I placed a 15 kilogram at 2 meter. Try to solve it. And write the result in the Discord. And also you can answer what is the reaction force here that can guarantee that this system is not accelerated in any direction. Yes, it's 3 meter because tau 1 nominal value has to be tau 2. That means R1 M1 has to be equal R2 M2, and from it you can calculate that this is 3 meter. What is this reaction force? You can find here the snapshots, so you can go back to my previous nice drawing and can find out, yes, exactly, it's 250, the same. Alright, that was not that hard, so now I will ask everybody to solve it, and also do not wait to someone they can solve it. And so let's say all of you will write the result. Oh yes, that makes sense. So this is a seesaw. The second part, you mean the reaction force? Alright, so let's look at the system. Let's look at the seesaw with two mass and so on, like a system. System can be combination of bodies. You can imagine like a big solid something. it has some mechanical part, it can rotate and so on, but this is one system. The F equal m times a is not only true for point-like bodies, but for system. If there are more forces in the system, we should put a force here. So that should be enough. What is the mass of the system? This m1 plus m2, since the other parts are massless. What are the forces? We have a g1, a weight 1, and weight 2. This is the positive direction. So this is g1 plus g2. Since they all goes to the positive direction, that means 250 Newton equal 25 times A, only considering the Newton's second law, it should accelerated by 10 meter per square. But this is not the observation. So if you look at the playground and see a seesaw, even sitting two children on it, it won't be accelerated with 10 meter per second downwards. Why? Because there is a so-called reaction force here, the force that holds. So if you look at this mechanics here, you can see these are massive elements, because it should be able to manage this reaction force. So this is very similar if you place a box on your table. There is a weight and there is a reaction force between the box and the table that stops to moving inside the table. Because if it's in rest, the box does not move into the table. That means there must be a reaction force. What is this reaction force here? This reaction force has to be equal, G1 and G2, but its direction is opposite. So if I go to the vector, the R vector equal minus G1 plus G2. But in the first example, we only calculated with the rotation of G1 and G2. Why does not rotate the R? Why don't we have to worry about what is the torque of the R? Because I created a screenshot so you can go back. See, so again, M1, M2, we can calculate the torque of G2, a torque of G1. What is the torque of R? This is the axis of the rotation. Since the level arm, the distance of the G1 from the M1 is R1, the distance from the G2 from the origin is R2. But what is the distance? And tau1 equal R1 G1, tau2 equal R2 G2. Why don't we have to worry about tau3, which is equal to R times something? Because the level arm, the distance between the force and the axis of the rotation is 0. So tau3 is R times 0, which is 0, so we can forget it. So all of the forces go through the axis of the rotation, won't rotate the system. So for rotation, we have to work only with the forces does not go through the axis of the rotation, but for translation, why it doesn't go up and down like a rigid body. For the translation, we have to calculate. So for the sum F equal m times A, Here we have to calculate with the r, but the sum of torque equal moments of inertia times alpha. Here we don't have to calculate with r, since this d equals 0. Right now, is it clear enough? All right, this is the practice. All right. Let's go back to basics. Physics is we measure something, we have some laws, some axioms. The board is too slow. I understand how. Yes. So it's hard to keep up. Yes. Oh. All right, let's try some other things. I open a paint. That will be and let's just pick up a pencil. Do you see it real time? So all right. Is it real time enough? No, I drawing this massless seesaw. Wow, it's very nice. Let's put a mass 1 here and the mass 2 here. There are two things. One is the translation and about the rotation. So translation. For translation we know the net force on a body or on a system, and this is the mass of the system, can determine the acceleration of the system. The sum of the torques of the system can be determined the angular acceleration via the moments of inertia. Alright, let's start with this one. This is the origin. Origin in this example is the axis of rotation. All right, how can we calculate? So what is the condition for being balanced? A balanced seesaw means the sum of the torques is 0, because if it's not 0, it will rotate, so it will move up and down like how the children playing in the playground. But if the sum of the torque is 0, it should be stay in this position. What is the torque by definition? Torque is a vector. We can get R cross F. This is a universal formula. But if we move in this plane, and let's say one force here is G1, the other force here is G2, the seesaw is massless, so we don't have to calculate with the weight of the seesaw itself. What is the R cross? So tau 1 is, well, R1, and this is R2. This is why we have to choose the origin as the axis of rotation, because otherwise this position vector won't be the right vector to do this vector multiplication. So how can we calculate it? This is one vector, this is other vector. If you use your right hand, so the A is the position vector, B is the force. Can you play that game? What will be the direction of R1 cross FG1? Wait, I try to manage it. So can you tell me what will be the direction of R1 cross G1 if this is R1 and this is G1? What will be the direction? Yes, R cross G, R1 cross G1. So do the vector multiplication of these two vectors. They are right now in the plane of the screen. Will it point to you? Will it be on this plane? What will be its direction? If you look at this right hand formula. No, I mean upwards is this direction. Try to place, so put in the direction of the R1 this finger, and the other, and the G1 is that finger towards the screen. I mean from the screen towards to you. I can write it here. So from the screen to you. So let's suppose, is it clear from this pointing? What is the direction of tau 1? All right. Yes, great. What will be the direction of this other force? If you play the same game, this will be tau 2. We don't always want to do this vectorial sum and so on, adding vector, subtracting vector. It's just long story. Why don't we, just a minute, why don't we choose a positive direction that can simplify your life? If this is the positive direction, and since one vector goes in that direction, other in the opposite direction, so if I say tau 1 is R1 G1, the nominal value, since this is 90 degree, you see the sinus phi, the angle between the force and this displacement vector is 90, sinus 90 is 1. So instead of vectors, we can use the nominal value of the force and nominal value of the position. That will be r times 1, and it goes into the positive direction. Tau 2 is r2 g2 and goes to the negative direction. So this sum of the forces can be simplified by tau 1 with positive sign and tau 2 with a negative sign. And that has to be 0, means tau 1 has to be equal to tau 2. And means R1 G1 equal R2 G2. But that's true only for this situation. So if, for example, we have a seesaw like this, with mass here, another mass here, we have a position vector, we have the mass, another position vector, another mass. Here it's not 90 degree. Here we have to use this formula. So it's only true for this balanced horizontal seesaw. All right, let's go for the translation. Translation means the sum of the forces equal the mass of the system times A. What is the sum of the forces right now? G1 plus G2, which is in the previous example 250 Newton, equal, this is massless and this is massless. So this whole system mass times, mass times A can be expressed like 250, it's not too easy to write anything in page, equal 25 times A should be 10 meter per square. So it's a must. From this translation, it should move, it should fall down with the acceleration 10 meter per square. But if you go to a playground, why don't you see falling into the earth? Why don't you see seesaw falling into the earth? What other forces? So this is a must. If we only look at the G1 and G2, it should move like this. It means we haven't found all of the forces for this example. Because if you look at very carefully for this system, there is a reaction force goes upwards. This is what I wanted to see. It's very similar when you put a box in the table. The box has a mass, it should have a weight, but the box does not fall into the table because there is a so-called reaction force, and since these nominal value are the same, so if this is 10 Newton, this is a 1 kilogram box, that will be also 10 Newton. That can, but in the opposite direction, that can guarantee that the sum of the forces on this system is 0. The box still stands on the table. Similar things here. There is a reaction force that can guarantee that the seesaw won't do any acceleration, won't fall into the earth. Wow, that takes time. Oh, stop it. What does it mean for this? For this equation, that means, of course, we have G1, G2. So you can't just delete the G1, G2 because it's there. We used to calculate the rotation. But there is also a reaction force. And if you go here with some tool, if you measure it, well, if you measure it, this will be the sum of these two forces, but the direction is opposite, so this part will be 0. That means the acceleration will be also 0. That's nice. We found the extra force. It's there. We didn't know it, but then we realized that there must be here, and if you go there, you can measure it. But if we have an extra forces, we have to come back here, because for balanced condition, we have to calculate with all of the forces that can cause any torque. But since this is the axis of the rotation, and this force, this reaction force, goes through the axis of the rotation, the tau from this reaction force is the distance between origin and the reaction force vector cross reaction force. But look at it. What is the distance between reaction force and origin? This is 0. So the torque from this reaction force is 0. That means in the sum, you can forget it. You only have to calculate with tau 1 and tau 2. Now, is it better now? Do you understand now? I tried to put somewhere this picture. I know it's a wow, why it is. It's not untitled, this is the seesaw. Yes, I mean, right now you are talking about R1 and R2, but I'm talking about G1 and G2. So the radius is meter, the force is in Newton. Yes, that's true. All right, let's do it on the next lecture. So I realize that that needs more practice. So right now I will have another course from in 5 minutes. So let's meet next Wednesday. Next Wednesday we'll have much more time and we can redo it again. But what do you mean by parameters? So does it help if I do not write any kilogram and meter, only R1, G1, and so on? I was thinking that it's easier to understand something with real number and not only writing characters everywhere. Which is better to you? All right, we will do that. So, thanks, you were very active today. I'm proud of you, even in this online situation. I, I can feel the feeling of the seminar right now. Thanks, bye, and the presentation I've sent to you, so you can look at it if it's help. Bye, and thanks again. You were very active today. I stopped the